Let's take a look at hashing passwords. Passwords should be stored not as clear text, just the plain readable password that you entered when you're registering with a website. Instead, websites should be storing a hash of your password. So we'll take a look at how this works. We're going to be using Linux for this. There's a few things in there that are helpful for us. One of the most basic things we can do here, we can hash a password, and we're going to do this in a very particular way. We're going to use printf space quotes pass 1 2 3, and then we're going to pipe that into SHA-256 sum. So the SHA-256 sum program calculates the SHA-2 256 hash, and there we get the hash. It should match what I see here in my own instructions, and it does. So this is better than storing, like if I registered with the website with the username Jim and the password pass123, not a good password, but we'll ignore that for now. The database should not store pass123. Instead, it should be storing a hash like this. But what if somebody else comes to the same website? Alice comes to this website, and Alice registers with the username Alice and the password pass123. Well, the exact same hash is going to be stored in the database. So when I log in, I'm going to log in with Jim and pass123. The website's going to calculate the hash and compare it to the database to make sure that my password matches the hash that they stored in the database. And if they match, I get let in. Alice does the same thing. But what if somebody gets my password for some reason and they calculate the hash and they say, oh my gosh, Jim and Alice, they've got the same password hash. What does that mean? Well, it means we've got the exact same password, and that's not good. So we can solve this problem. We can salt our passwords. Salting is part of the solution for the password storage problem. So let's say I want to use the password pass123. Not a great password, but I'm going to do it. The website might generate some random data, which we would call salt in this case. So let's say that that random data is 56123. Dot. I'll just put a period there just to separate the salt from my password. In reality, that dot would be part of the salt, but hey. Then it's going to store that hash in the database. So now it would record both my username, my password hash, and the random salt that it created just for me. So kind of them to do that for me. And what if Alice registers? She's going to get different salt. So even if Alice uses the same password, pass123, because she'll have different random salt, her password hash is going to be stored differently in the database. So far, so good. These hash functions work the same as hashing files. They're just taking data and producing the hash. In this case, they're just taking a couple of characters as input and producing the hash output. We can add a little bit of salt to add a little bit of randomness into that process to help make sure, even if two people use the same password, that the hashes will be different. So this is what a database could look like, a trimmed down database. We've got usernames, we've got some salt for each of those users, and we've got their password hash there. So did two of these people use the same password? Just looking at this, I can't tell. I know they did because I created the table, but it's the same pass123. So salting is good. It helps protect user accounts so that even if somebody gets access to our database, it's a lot harder for them to attack these hashes to try to discover what the passwords were. Now, when we hash files, we want those hashing algorithms to go just as fast as possible. Speed is good. If we can, so modern chips have many of these hashing algorithms built into your CPU so that they can happen the calculations can happen very, very quickly. But if somebody is trying to hack our hashes to crack these hashes, speed is our enemy. Because the faster they can calculate these hashes, the faster they can try to break our hashes. So we don't want that. There are better algorithms out there. One of them is called bcrypt. So we're actually going to go into Python now inside Linux. So we're going to launch Python 3, Python version 3. Lots of Linux systems have Python version 2 and Python version 3 in the same system. So we want to make sure we're using version 3. So even if you don't know Python code yet, we haven't really talked about it yet, just copy down this code. We're going to import bcrypt. So the bcrypt library has all of that functionality. I'm gonna be lazy. I'm going to copy that line of code. You can right click in your browser and paste as plain text, and it'll write that there for you. Let's take a look at what happens when I press enter now. Notice there was a very small delay. It was small, but it was a meaningful delay. It actually took, a non-trivial amount of time to generate that. I know it seemed really fast, but let's take a look at this output. Here is my bcrypt hash. There's some version information here with some data about the hash. So this $2b, that's the version. It's the bcrypt version that we're using. 12 is an adjustable work factor. So what this algorithm did was actually slow itself down. The higher you make that adjustable work factor, the slower it goes. Next, there's salt. Salt is part of this algorithm by default. You can't use it without salt. So we see this line here. We told it to generate the salt for us. That salt becomes part of this hash output here. And then the rest of it is the actual hash. It can be hard to tell just visually looking at it where the salt ends and the actual password hash begins, but just know that it's in there. It's all embedded in that one hash. Now, when we used SHA-256 and we generated the hash for pass123, you do it 1,000 times, it's going to be the same every single time. But here in Python, if I hit the up arrow key and I hit enter again, the same pass123, I'm asking it to create some new salt for me. The hash is going to be different. We still have the same version, same work factor, but the salt's going to be random, and then the resulting hash is going to be different. So bcrypt is good for two reasons. One, it salts everything by default. Number two, it can run slow, which is good for hackers. If you're trying to crack hashes, like you've got hashes and you're trying to figure out what password made that hash, if somebody used the SHA-256 algorithm, they can try to crack those fairly quickly. If somebody's using bcrypt, it's about 1,000,000 times slower, much, much slower. So if it would have taken a year to crack the SHA-256 passwords, it would take 1,000,000 years to crack the equivalent bcrypt passwords. So we can generate this multiple times. Notice that very slight delay, even though it's just a couple of milliseconds, it is meaningful. Let's take a look. I'm going to open up a new tab, and I'm just going to Google Cyber Chef. And it's in my history, so it took me to the Cyber Chef here. Let's take a look at that adjustable work factor just a little bit more. So pass 1, 2, 3 is my input. There I've got the output as pass 1, 2, 3 because there's no recipe yet. In the operations, I'm going to search for bcrypt. And I'm going to drag bcrypt into my recipe. Notice it says rounds here. When we just did this in Linux, it defaulted to 12. This particular website's defaulting to 10. Not a big deal. We can take a look at how long this took. And it's telling me it took, old man eyes, got to get closer to the monitor, 100 milliseconds. What if I change those rounds to 12? Boom, boom, to 12. We're at 325 milliseconds it took to calculate that hash. If we make this even bigger, let's go to 16 just for funsies. Notice it's thinking about it. That slowdown factor is really doing its job. That took 5.2 seconds, so 5,000 milliseconds to run. Now, what that would mean is if somebody's logging into a website, when they enter their username and password, if we were using 16 rounds here for that adjustable work factor, 5 seconds of that user waiting for the page to load is just this algorithm running. Now that might be a little bit too high for most of our users. We might not want that to happen. So we'll choose something a little bit lower. A few fewer rounds is a good balance of performance from the user's perspective and security in our database. Let's drag this off. Let's compare this to SHA-2. So I'll put SHA-2 into my recipe. If you have a recipe, you can hit the trash can to clear your recipe, or you can just drag something from your recipe just off to the side to get rid of it. Let's do SHA-2 with the 256 variant, because that's what we did in Linux just a second ago. How long did it take to hash pass 1, 2, 3? This took 14 milliseconds. And if I click bake again, look at that time. 1 millisecond, 1 millisecond, 0 milliseconds. So this is dramatically faster. SHA-2 is built for speed, and it does it really well. So we can add more input there. It's still hashing it just almost instantly. So this is what systems do to store your passwords. A good system is going to be salting passwords. Salt is just some random data being added to the password that ultimately gets hashed. SHA-2 is used frequently in a lot of systems, partially because the United States government has endorsed the SHA-2 algorithm for use. But I think increasingly over time, we're going to see these slower algorithms, slower intentionally, slower as a feature, like bcrypt, storing passwords in a lot more systems. We should never store passwords in clear text.